Hello everybody. In this video we are going to talk about some network communication testing. And so I've got a scan tool, a breakout box, PicoScope. We'll look at two different types of network communication that are commonplace. This particular Nissan has a K-line serial system for its data, and then we'll look at a CAN system on a newer vehicle as well. So here we've got a handful of tools that we could use if we were going to look really closely at network communication. One of the great tools to do that process is this thing here. This is a breakout box. And so the other end of this cord is going inside the Quest here. It's connected to the data link connector. It provides me a set of pins, all 16 of the DLC, where I can make connections. And then the other cool upside to this particular breakout box is that I get an LED light around the ones that have activity at the time. So I can see that I've got power into it. I've got a good ground at these two ports. Pin 16 has got constant battery. And then I've got another port at the end here so I can hook up a scan tool. So I'm going to hook up my scan tool and set this aside. And so when this is hooked up and things are going, you can see that there is some activity. I'm going to go ahead on the tool, go into my vehicle history and get the Quest selected. And so one of the easiest ways that we can create data flow and data transmission is to go on a scan tool and go to the PIDs and live data. And so here you can see the K line, which is pin 7 on this, has got some activity as it flashes back and forth. So now on my scan tool, I've got RPM, O2s, just some general PIDs. And you can see that I've got activity here. So what does that tell me? Where would I use this in diagnosis? It helps me understand that there's a good connection on the data network. Data network faults have become increasingly more common. As we add more modules, we add more lines for data. And so with that increase in wiring provides an increased occurrence or chance that one of those wires gets disrupted. We'll go a little bit deeper with some of those faults as we talk about CAN. So one of the things I want to do is show you what serial data looks like. So I've got my Pico here. I'll go to a ground and I'll go to the K line, and then we'll switch over to the screen and see what that looks like. So here's our trace and waveform for this K line. I've got it zoomed out pretty far. But each of these occurrences that we see floating by are packets of information. So anytime we have information that's transmitted within a serial system, or really any electronic data system like this, we refer to those as packets. And so if we go and pause this, I'm going to go back a frame or two until we get one of the packets, and we'll take a closer look. All this packet is digital communication, right? So because it's digital, the only changes I've got in this waveform are on-offs. And so I'm going from 13 volt down to 0. And so this is a full source voltage just switched on-off. And so the on-off ultimately translates to 0s and 1s, which helps me translate that computer language so that we can communicate things like engine RPM or the ECT value, the things that are on my scan tool screen right now. That information is all in this packet that you see on the screen. At the automotive technician level, we really don't look to understand exactly how to break these down. If you really get into the engineering side of these things, there is software out there that you can get where we could take this kind of information and begin to decode it to get to the point where we understand that exactly which piece of this snippet and packet is RPM. And so if I was developing maybe a plug-in unit that would display RPM on the dash, those are things I would need to know, right, as the engineer developing that. As an automotive technician, typically just looking to restore a vehicle to fix a problem that has impacted operation, I'm not generally going to go to that level. And so the things that I do want to look for as a technician is the voltage that I'm working with. Do I have a full source voltage here? Am I going all the way to 0 here? Because those things help me understand basic electrical faults and occurrences, which typically are the things that bring me trouble, that if this K-line signal was to get grounded or had some kind of resistive ground, it may change that voltage and bring it down. Those kind of partial voltage changes are much more of an issue in CAN systems, and we'll look at kind of how those are developed. Those are a bit different. But again, with my K-line kind of set up like this, I'm really looking for kind of a go or no-go situation. The other thing that helps me with the PicoScope is that I can look at the main data bus to the ECM, like we're doing here, and then I can look at it for other modules. So depending on what the daisy chain of wiring is, that can help me understand where I need to find a fault. So if we had a vehicle that had a serial communication fault, so say we had a U code that was looking at a particular module for lack of communication, one of the things that I really need in order to understand that sequence and make determinations about where to look is how that data bus network is wired. And so a lot of data bus networks are put in somewhat of a daisy chain where the main line of communication goes from the data link connector straight to the ECM, and then other modules down the line are connected kind of on the other side in their own clusters. So a diagram like this can help me understand that. And so this particular one's got the data link connector down at the bottom. We're working with pin 7 on our breakout box. And so we could track that up. That's got a direct line to the engine control module. And so if I had a U code for the engine control module to say the trans control module, I begin to look at where are these connected. And I see pretty quick that the serial communication lines are separate from the K line that I'm using on this breakout box. That's an important thing to distinguish, because checking the K line on this breakout box is not going to help me with that fault. So finding the roadmap and the daisy chain of this network on any particular car is really a critical piece in trying to diagnose communication faults. So if we wanted to interact more readily with those other lines that go to the trans control module, you'll see that these are connected, right? So the serial communication lines for TX and RX, so that's transmission on the TX side, receiving on the RX side. And so serial communication uses one line to send out, one line to receive. So on this one, I could go to the receiving line is pin 13 on my breakout box. So if I come over here and I'm going to move this pin over to 13, we'll come back to our PicoScope. And so here we've got some really small pieces of information coming by. What we'll do on the scan tool is see if we can make that more prevalent. So I'm going to go on my scan tool and go ahead and select data within the transmission control module. And then we'll go back to the PicoScope and we'll see what we've got here. Huge change in communication and activity. I need to turn off my auto scale here. So the screen is really having a hard time selecting what to look at because I had it on auto. We're going to change that. We'll kick it over to a 10 volt scale and we'll look at more time so that we can see what's going on. So I'm going to go, while that loads, we'll notice there's a big difference in this serial communication line versus the K line that we saw on the breakout box at the DLC on pin 7. This one is only running at about 3 volts, which is pretty typical. Serial communication is a low voltage communication, and so it utilizes a separate lower voltage to make that happen. Right, so right there you can see this is activity from the scanner trying to make contact with the TCM. And if you notice, I gotta go way down here to see what was going on with that. The transmission rate was quite high on those. All right, so here's my scan tool. I switched modules, trying to communicate here with the ABS module. And so you can see a lot of activity that's taken place. We'll go ahead and pause one of these and zoom in so we can get a closer look. So again, this is on a low voltage scale. It is still digital communication So here, this was some communication with the ABS module. So we switched over to one of the other modules on that daisy chain. And from here, it looks like a lot of noise. I found that it can be challenging to get a really clear picture of serial communication with the PicoScope. Some of that could be my setup. Some of that could be the way that the Breakout Box is developed inside. And so it's typically quite noisy. There's some active filtering things we could do. But for us at this point, it does convey the idea that those lines are carrying communication. And so I can see that there's activity. This was a result of me using the scan tool to ping and kind of summon information from that module. And so I can see that response all the way through the whole network. And so that's a good sign for us if we were chasing some kind of communication fault. All right, so we switched over to the 2014 Silverado. I've got a similar thing set up here from what we did on the Quest. The biggest difference in the Silverado, being that it's a newer vehicle, most vehicles post 2008, pretty standard to have CAN communication, so controller area network communication. And this is a different form of communication. It utilizes a high speed or a high and a low, and it is a much higher speed or higher rate of data transfer. The good thing for that is that because the sophistication that we're adding to all these modules and systems, their need to communicate in real time with large information packets has increased. And so CAN has really satisfied that up to a point. And so we'll take a look at what CAN systems are designed to do and how they communicate. So on here, I've got a handful of things plugged in. I'll move some of them so we can take a look. So if we look, this Breakout Box is really great in that it's got a lot of notes. And so standardized CAN pinouts, you can see some of these say of SAE. And so that tells me that that's a standardized connection. And so 6 and 14 are the typical CAN communication pins on a DLC. They are the standardized pins. And so 6 is the high, and then 14 is the low. And so if we start with that, I've got 2 channels going on my PicoScope. I'm going to go ahead. I've got both my grounds just stacked together. Real nice thing about PicoScope connections here and a lot of scope connections. I can piggyback those. And so then I'm going to go to just pin 5, my signal ground, leave that connected as my reference. And then my blue is my A channel, red is my B channel. I'm going to go ahead and put my A on the low side, or the high side of things, which is pin 6, and then low side, which is pin 14. And so now if we go back to the screen, we'll get this zoomed in. So here we've got communication happening. I've got a scan tool hooked up here just doing live data. So we've got some things happening on the network, some extra communication. If we get these pulled apart, we'll be able to see each of them. So CAN low and high transmit the same information packets just at different voltage values, different voltage levels. The reason for this redundancy is to help prevent any kind of electrical fault, a resistance, an open circuit, a short circuit. If any of those things were to occur, then we could potentially lose one or the other and still have functionality, versus if I lose all communication with most vehicles, a network that is open circuited will result often in a crank no start or no crank. So that's where we see some issue with network faults, is when we get to that level. But if we just had a fault code so a U code for some kind of communication fault, this would be a great test for me to do, just to see where are my voltage values, do I have consistent packets, and typically I can learn some information from that. So on this, again, sometimes difficult to get clean values. All right, so we're back on the screen here. We've got our high and our low. We'll get some of that separated a bit so we can see better. I'm going to go ahead and turn each of the channels up to 16-bit resolution, just to give us a little bit more vertical resolution. And so here I've got these laid on top of each other, and there's a trigger over here. This is my yellow dot. That's my trigger to kind of keep these indexed and keep a flow that's occurring. And so I'm going to split the screen a little bit here, and we'll pause it. So one of the challenges that I've had with this breakout box is getting a really clear cut signal. And so this one, not the best example, but I do have some fairly defined on-offs, which is what I'm looking for. Canned communication is a digital form of communication, and I do expect just to see on-off switching that helps transmit those packets of information. The other thing that I'm going to look for on these is that the low and the high mirror each other. I should see this repeatability like this as I go through that transmission. If we go pull the example waveform that PicoScope has, that'll save us some time from chasing our connection issue here. This is a better example of what we expect to see, and really what I think is occurring on this truck. I'm just having a poor time getting the connections without noise and interference. So here you can see really sharp on-offs, very consistent voltage values at the top and the bottom. That's critical and that's important. And so if I was looking at this from a diagnostic end, that's really what I'd be looking for. And so on this particular truck, the other thing I wanted to show was how these things are put together and some of the different data networks that exist on it. So this here is my data link connector. These are the two pins we hooked up to. So I've got 6 and I've got 14. Those go to splice packs and then go over to these 2 wires. And so on this particular truck, this is the low speed CAN. I take that back. This is the high speed CAN, excuse me. And you can see all the different modules that it links together. One of the other unique things about CAN being that it's a 2-wire communication, those wires are actually tied together with a resistor at each end. We refer to those as the terminating resistors. And so I've got one down here, terminating resistor, high-speed bus, and one here at this other end. The low and the high then run in parallel through all the modules to connect them together. The good thing about this is that because they have a terminating resistor, if this wire was to get shorted to a power source, that resistor should help us save some modules. The other thing that is great from a diagnostic end is that if I've got 2 120 ohm resistors wired in parallel, I expect to see 60 ohms if I put my ohm meter across that. So let's switch over, we'll set up, and we'll take a look at that test. Okay, so I've got my ohm meter set up, and my 2 leads, my breakout box is still connected to the truck. I'm gonna go put 1 lead on pin 6, I'm gonna put 1 lead on pin 14, so I'm across my low and my high speed. And we can see there I've got just about 60 ohms worth of resistance. And so that's a good sign that shows I have connectivity between pin 6 and 14 to both of those terminating resistors. And that tells me that the general health of that wiring is pretty good. This is a good short test to do if I had a network fault, just to confirm the viability of the operation. And then from that point forward, I would have to go on to individual modules and do checks from there. There's some really cool tools that exist for doing those checks. One of the cool tools that exists for doing these kind of checks on the General Motors side, so specific to this truck, General Motors developed this tool called the Data Bus Diagnostic tool. It's part of the GDS2 and kind of MDI platform, and it allows us to connect with my MDI and basically ping individual modules, and it will emit an audible sound based on what's happening. And so the good use for this tool would be that I could set this up, have it ping all my modules, and see who can come back with a response and who can't. And so on a vehicle that has a lot of different modules, especially in daisy chain or a gateway that serves many modules, it gives me a quick rundown of who can communicate and who can't. And then I can create a diagnostic plan from that to say I only need to spend my time on the wiring and tracing of this particular module. And so it's trying to cut down on just the physical time of tracing wires for communication faults between the dozens of modules that exist on a lot of vehicles. So that's a short rundown on data communication and some of the practical testing we could do just to ensure that we've got good connections and some viability for our network communication. I hope it's informational. I hope it's helpful. Thank you.